Hi everyone. Welcome to this presentation from Epidemic Sound. We will talk to you here today about audio-based similarity search. Let us begin with an agenda. As an introduction, I will walk you through what we do in the machine learning engineering part of Epidemic Sound. Then I will hand it over to Oscar here, who will talk more actuals about the similarity search, what it is, how we built it, and what we learned. And finally, we will end with the lessons learned. My name is Johan. I'm head of machine learning engineering at Epidemic Sound. Let us begin with the machine learning engineering part. Or rather, actually, let us begin with Epidemic Sound. What is Epidemic Sound? It's a subscription-based music platform where you can get access to a lot of music without any hassle of royalties. And what do then the machine learning engineering department do at Epidemic Sound? Well, we have a vision that is like this. We think that we should accelerate innovation at Epidemic Sound, and we should contribute to robust scaling of the company. And we should do it in such a way that it's mature and responsible. We have chosen to define our mission like this. We want to use machine learning and data to create outstanding products. We are product-centered. We are not into insights. That's what analytics does. We also do collaborate, of course, with analytics, and we formulate it like this. We contribute to efficient business practices by using our domain expertise and best engineering practices. Let me show you some examples of projects and initiatives that we have in the company. On one hand, we work on recommender systems. We want to recommend tracks to our users so that they in turn can use it to create beautiful creations. And this is the standard problem where you want to grow with your users. You want them to continuously make use out of our services as they grow with us. Another more specific topic that is special for us is metadata tagging, we chose to call it. Music has lots of effects in it and parts that you may want to use either as input to something else, or you want to identify perhaps drops, beats, and other such musical elements that you want to use. And this is a big topic for us, and we are putting lots of efforts into getting good at this. On the other side, we also work on curation tools. How do you create effective playlists, for example? How do you bundle things together? And we have more specific projects, like let's say a user uploads a video. How would you go about soundtracking this in a good way? And finally, we have the more classical topics, of course, the growth cases. Everyone wants to have software that helps them forecast and to build efficient decision-making systems. But these aren't the topics for today, sadly. We're instead going to focus on this blue topic here, the audio similarity. Actually, without telling you more, I will hand it over to Oscar. So thank you.
Cool. Thank you very much. So what does this even mean? As Johan alluded to, our chief product is letting people have access to our large catalog of music without the hassle of royalty. And as of last week or so, our catalog consists of about 43,000 tracks. This amounts to about 3,000 full-length albums, and I think you'd be hard-pressed to find someone who has actually listened to all of it. We're working very hard to make sure that our users don't actually have to. So we're trying very hard to ensure that our catalog is tagged, searchable with genres, subgenres, and moods. And while this has worked pretty well historically, we kind of decided that this is not enough, which is where this project comes in. So the overarching idea is that if you have an example track and you know how this sounds, we want users to be able to find tracks or parts of tracks in our catalog that sounds very similar, but without having to go through the hassle of actually trying to describe it. We want to help our users answer questions or statements kind of like these. I like the drop of this track, but I don't know how to find more like it. I'm not really sure what genre I'm listening to right now, but the vibe in general is what I want for the video that I'm making. Or just in general, like it has a nice outro, and that's what they need for their video. So here's to hoping that the demo for this is gonna work well. Pre-recorded because we're scared of live technical demos. Almost. And this is already at the end of the video, also without sound, which kind of defeats the entire purpose of audio-based find similar. We pre-recorded so that we wouldn't have technical difficulties.
We are too optimistic.
Yes.
Shall we sing a song, Oscar?
No, I don't think they want
This
that.
time. We do care about creativity, though, but perhaps this is not the proper place to exhibit it. Shall we describe the tool, what it's trying to do?
Sorry? Do?
No, what do you do?
Well, that's a bummer, but these things happen. It kind of. Let's show the image at least, so we can visually describe what the tool is trying to do at least. Right, so this is a screenshot of our website, and this is the main page where people go to find our music. We have various ways to browse the catalog, and within this tool, you will have access to the waveform that describes the entire track. Using the selectors in the interface, you can decide which part of the track that you are the most interested in. And the search engine will then take that part of the track and try to look for other tracks in the catalog that sound similar. And I'm looking at him browsing for files right now. Yes. Go ahead. We have some. We now have some time to kill. We are going to get into that, but spoiler: we are looking at log-mel spectrograms. And the musical features at this point are quite implicit. We do not perform deeper like musical structure analysis for this implementation of the search engine. Yeah, you like the triplets, so you get more of them. Maybe they think that you're a huge fan of waltz. Right, so we allotted about 3 minutes for the 3 demos, and I think we are kind of running out of time to try to fix this. I actually do. if there was a way to just cast to this computer. But I think to be mindful of time, let's go into the technical details.
Let's maybe do a demo afterwards.
Yeah.
On the phone for those of you who want.
Yes. So just catch us. Luckily, it's lunchtime after this, so and not to impose on your break time, but we're available for private demos afterwards. Right. So the basic principle of this, we have an audio clip, a musical clip of varying length that we somehow want to run through an encoder in order to create a low-dimensional embedding space such that distance in this space has meaning. We are leveraging a triplet loss, one of the many variants of the triplet loss that I believe were popularized around 2016 by FaceNet, in order to try to encode clips in such a way that we can determine similarity between them, right? And we're doing this in the initial version. We leveraged a lot of music production knowledge in order to design rules for what constitutes similar and dissimilar audio clips for a given clip that we start with. And this puts the similarity notion explicit in the code, which gives us the ability to control all of these notions. So within the triple loss, there are three parts that make up the main structure. We first have the anchor, which is the starting point, the clip that we want to analyze. And then we also have the notion of a positive and a negative example. Within this loss function, we are trying to make the difference between the embedding of the anchor and the embedding of the positive example as small as possible. Whereas we're trying to increase the distance between the anchor and the negative example. In the initial version, we mainly achieved this by using train time augmentation of the anchor clips. But we have also moved on to leveraging all the metadata that we have in the catalog. All of this is done mainly within mini-batch sampling. And the train time augmentation lets us force at least one positive example in the mini-batch. Having a large catalog of metadata, such as the track identifier, the genre, subgenre, and mood, lets us construct additional triplets, which we can then weight together into a final sum that then produces a scalar loss function. This lets us hyperparameter optimize for which of these different parts should constitute the biggest contribution to the loss function. This is supposed to be straight, but it's not. It fits the theme of the rest of the presentation. These are the music production motivated augmentations that we use in order to produce positive examples. So starting from an anchor clip, we can shift it in time. So we're looking forward and backward from the original clip. We also decided that pitch shifting, like raising and lowering the tone of the clip, as well as time stretching, which gives us a little bit control over the tempo of the clip. That if we fiddle a little bit with these, that this should still constitute a positive example, and these clips should be close to each other in the final embedding space. We're also using reverb and additive noise. Reverb is just a fancy word for echo. And it works a little bit like a blurring function. The additive noise is a common way to just make the encoder a little bit more insensitive to noise anywhere in the production chain. Right, so to be mindful of time. You've seen a slide like this, I bet, a million times if you've been to a conference like this before. But I want to focus on a little bit on the embedding serving part. So I really wish the demo would have showed, because it shows kind of how snappy the final search engine is. But we, given that we have 43,000 tracks in our library, and we want to index each track upwards of a couple of hundred times, this gives us an embedding space that is in the order of millions and billions. And this, in turn, is what we then query against when we're looking for similar clips. We're doing this by leveraging Elasticsearch built-in nearest neighbor functionality, which, according to them, I think we're the only people in the world who actually use it for this. They are kind of raising their eyebrows and when we're telling them about this. But it works super quickly for our purposes. And that's really one of the more important parts of this entire project. If it wasn't fast, snappy, and a pleasure to use, if you would have to wait a couple of seconds every time you change the slider, you would probably get annoyed and go back to regular text-based search tools. Right, so modeling choices. This is a large list that I'm trying to put out on the screen. I'm not going to go too much into detail about this, but what we found is that for our purposes, defaults work super well. librosa is what we use for yeah. I'm losing my train of thought as we're getting a little bit stressed here, but in general, we made a lot of progress without actually trying to optimize for a lot of the parameters that we have to work with. This still gave us a super nice starting point for this project, and it turned out into something that we're pretty happy with. No good machine learning project is actually good without a simple baseline. So we decided on a random encoder, which generates a random embedding of the same size every time you send a clip to it, as well as the MEL frequency, let me try to pronounce it, Cepstral coefficient, also with librosa defaults, just to have a nice way to compare our trained model with. And as we have decided that, in the embedding space, this turns into a kind of a ranking problem. So we decided to leverage the mean average precision metric in order to get a kind of an overview over how the training is going. And it turns out at least we can beat the baselines. But here's the kicker, I guess. Music is super subjective. Can we actually decide that these metrics mean that people who are looking for music for videos are finding what they want? That the notion of similarity translates to what they expect? And it turns out that metrics aren't everything. We make an enormous use of user testing. We have a couple of really thorough people who have showed this to our more experienced users, conducted interviews, sat for hours and hours to talk about what is it that is actually showing up and are you happy with it. And really without them, we could just look at the numbers and say, yeah, this is probably good. Let's ship it. But I think that's the point that I want to really point out here, as we are reaching 17 seconds left on the clock. we're kind of academically inclined, so we're super happy to share the articles that we have used in order to get this project going. And yeah, thanks for listening. That's time.